This is Miss Hughes, and today we are looking at two important definitions and one important technique for probability. The first definition is for the phrase mutually exclusive. So two events are mutually exclusive, basically if they can't happen at the same time. Here's an example, and we're going to look at how to apply this rule here. We've got numbers that are written on pieces of card and placed in a bag, and one number is selected. One card is selected at random. The first instruction is to draw a Venn diagram. So here we've got A, which is the primes, and here we've got B, which is the evens. Let's go through each number. So 3 is prime, but not even. 4 is even, but not prime. 5 is prime, but not even. 6 is even, not prime. 7 goes here. 8 goes here. 9 goes here, because it's not prime, and it's not even. And 10 goes here. Alright, and you can see already there is nothing in the middle. 2 would generally be in the middle, that's the only even prime number, but 2 is not on the list. So, determine whether mutually exclusive. Well, they are, because the probability of A intersection B is 0. There is nothing there. The second definition is for two events that are independent. And we're going to use this rule here with this example. Again, it's the same situation, but the numbers are a little bit different. And the sets are also different. So the one on the left, is odd numbers. So A is odd numbers, and B is the square numbers. So again, let's go through each number. 2 is odd, not square, so it goes out here. 3 is odd, not square. 4 is square, but even. 5 is odd, not square. 6 is even, but not square. 7 is odd and not square. 8 is even. No, 8 it goes out here because it's neither odd nor square. And 9 is square but odd. Okay? If necessary, press pause and make sure you know why all these numbers are placed where they are. Now, we're going to see if this rule applies to see if those two are independent events. So let's first of all look at probability of A intersection B. Well, there's only one number that is in that intersection out of 1, 2, 3, 4, 5, 6, 7, 8. So the answer to the left-hand side is 1/8. If we look at the right-hand side, probability of A is 1, 2, 3, 4 out of 8. So there are 8 numbers. And probability of B is 1, 2 out of 8. Now if you multiply those two numbers, we get 4 out of 8 times 2 out of 8, which is 8 out of 64, and that simplifies to 1/8. So we get the same on both sides, and that shows that events A and B are independent. Alright, and lastly, we've got a good technique called sample space diagram. A sample space diagram is a diagram that shows visually all the possible things that can happen when I look at two different events. So here's an example. We're rolling a blue dice and a red dice, and we're looking for different probabilities. So the first one is the probability that I get a total of 7. The ways to get total of 7, it can be 6 and 1, 5 and 2, etc. So all of these give me a total of 7. I think that covers all of them. So probability of getting a total of 7 is 6 out of, well, the diagram shows that there are 6 times 6, 36 possible things that can happen. So that's 1 out of 6 if we simplify. For B, we're looking for the same scores coming up on both dice. So that's a 1 and a 1, 2 and 2, 3 and 3, etc. So there are 6 probability of same. 6 out of 36. Again, 1/6. For the next one, we're looking at the difference between the scores is 1. So that could be a 6 and a 5. A 5 and a 6. A 5 and a 4. A 4 and a 5. Etc. You can see that you can actually see that there's going to be a pattern. So all of these pairs that I'm drawing, the dice have a difference of 1. Okay, and if we count them, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So probability of difference of 1 is 10 out of 36, which we can also simplify to 5 over 18. All right, 2 to go. So the next one is probability that the score on the red dice, let's just clear this a little bit. Probability that the score on the red dice is less than the score in the blue dice. So the red number being smaller than the blue number. Okay, so that is 1, for example, a 1 and a 2, a 1 and a 3, so all of these, and then a 2 and a 3. So all the ones I'm colouring have the red dice being smaller than the blue dice. And if we count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So probability, let's go back to red. Probability, purple. Probability of red less than blue. What do we say? 15, right? Out of 36. We could also cancel that down to 5 out of 12. Okay, and last but not least, the probability that the total score is a prime number. There go those primes again. So totals that are prime. For this one, I think if this were an exam, I would actually take a bit of time just to list all the possible totals. So 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, and so on. So each time I'm adding the score of the blue and the red dice. 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. So we want the times when the total is a prime number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So, same as the previous one. Probability of total prime is 15 out of 36. And that is the end of